So good morning, everyone. So after 2 weeks in Mallorca, maybe you want to go to a much colder place, such as. So let's move to the polar regions once more. So if you want to visit polar region, you can take a ticket on a tourist boat, but then it may be a bit risky. And this is an example of a cruise ship that was going around Antarctica and that was eaten by iceberg that was hidden in the sea ice pack. So they sank in a matter of a few hours. Hopefully no one died, but it's a kind of risky place. So if you want to be a bit safer, you can also try to go on a nuclear icebreaker. The Russian ones are the best in the world, but then the ticket is much more expensive, like maybe 1,000 times more expensive. So maybe sea ice forecasting could be useful for those guys to avoid such catastrophe, but also to reduce the cost of operating in ice-infested area. So that's what we wanted to do something useful for them. But then the first question to ask is, what do they need? What do the users need? I think it's the best question to start from. So first, you need to know who they are, what kind of ship they use, things like that. Then you also need to know where they go. And this is an example of the ship tracks density for Kawasi. So it's in the Arctic. You have the Siberia over here. And you see all these tracks are coming from ships. It's from 2 years, so it's the track density for the last 2 years, and it includes summer and winter. So of course, in winter, there is much less people going in this region, but there are still people going in ice-infested region with any kind of boats. It could be with shipping boats, tourist boats. That could be also to do some drilling and exploration, and also shipping. So that's more or less all the potential clients we have. So then the second question to ask, so we can ask them, is what do they use at the moment when they do planning and when they try to avoid ice when they plan their mission. So to answer that question, we just read some reports, and this is the conclusion from a very nice report. There is the reference below. And the conclusion from this report is that microwave-based maps are actually useless. That's the word they use. Because in summer, there is melted ice on top of the sea ice, and those microwave-based satellite data, they think that there is no ice at all. So it's only melted at the surface, but they think there is no ice at all. So that's one problem. The second problem is that when the ice is too thin, like less than 50 centimeters, they also consider that there is no ice. And the third problem with the microwave-based data is that when there is a large variability, so low concentration somewhere, the signal is all mixed, and they also consider that there is no ice. So they said it's useless especially for vessels with low ice class, so the one that want to avoid any ice. So what they use actually for planning is more ice charts, and there are two types of ice charts. Either the one giving only 2 classes of ice concentration. So this is an example from the US NIC, so National Ice Center. So you have a limit that gives you the open water limit. So it means that behind that there is no ice at all. And then they give also a second limit that gives you the limit for the 80% concentration ice. It's based on many different satellite products, but it also includes SAR information from SAR. And that's why they can see much more sea ice than in this type of product. And then there are also multi-classes ice charts that give you much more precise information for different categories. So for example, from NIC, you get a category from 0 to 20%, 20% to 40%, and so on. So that's very useful, even for icebreaker, because they know how to avoid the highest concentration. So that's very useful to reduce the cost and to do planning. But then when they are really in the ice pack, they use another type of information. They use many SAR images that are directly downloaded on board and read by the captain, or that are analyzed by specialists to try to identify two important features. The first one are the leads. So the leads, it's the fractures, the open water. Because if there is a lead, you can just go in the lead, follow the lead for many kilometers, with much higher speed. And then they also try to identify ridges. So from us, we are not trained to do that. So I cannot say where are ridges and where are the leads, but people trained to do that can do it quite easily. So this is an example coming from a Norwegian company operating icebreakers in the Arctic. And in this example, they were using this type of image to follow and to guide the Thor Viking icebreaker. And you can see the track of this icebreaker on the SAR image. And they were quite happy to cross the track of a Russian icebreaker, which is over here, because then they were able to just follow the Russian icebreaker. So the ice was already broken. It was much more easy for them to just follow the same track. So this is these are the two types of information they use at the moment and they trust: ice charts and SAR images. So to convince them to use our forecast, what we should do is to show that we can beat ice charts persistency, so that we can provide better information than the latest available ice chart. And also, we need to convince them that we can forecast local deformation a few days in advance. So if you have a SAR image, it's often there is often a few days of delay. So it's an image of the paste. And that was also a question raised on Tuesday. Can we forecast sea ice deformation days in advance? So if we can do that, we will convince them that the forecast is useful. But there are also other issues with sea ice forecasting, especially when you do data assimilation. You cannot directly apply methods developed or used for the ocean and the atmosphere directly for the sea ice, or at least that's what I think, for three main reasons. The first one is that in the satellite products available for sea ice, there are systematic biases. So you have to take those biases into account. It's not just a random Gaussian noise around the mean. Also, the sea ice forecast systems are open systems. Usually they are forced by external forcing. For example, they are forced by the wind from ECMWF forecast and so on. So you are also potentially affected by biases in the external forcings, and you should also take that into account. And then there are also many discontinuities due to the complicated sea ice dynamics in all the sea ice fields. So you need also to take that into account when you do data assimilation. So I'll start with presenting the NeximF platform. which is one of the applications of the NERSC model. So it's the model I briefly discussed on Tuesday. We start developing this model only 4 years ago when Pierre Rampal and me joined NERSC. So sea ice forecasting is one of the application. We do also sea ice ocean interaction and biology in or below the sea ice. We have some projects running on developing new Lagrangian data assimilation methods. We also work on sea ice remote sensing. And finally, we have some activity on the interaction between waves and sea ice. So that's all the activities being done with the model. Some of them are funded, supported by public agencies such as the Research Council of Norway, ONR, ESA, EU, and the Bjerknes Center. And some of them are supported directly by the industry. So we had some funding from Total for the sea ice platform, sea ice forecast platform, and also we got a project from the oil and gas producers to look at pollution in sea ice, so oil spills in sea ice. So the NERSC platform, it's a sea ice only forecast. It's a sea ice only forecast platform. For us, it's more a tool to play with sea ice forecasting and to play with the model. For them, for Total, it's a source of information for planning operation in Kara Sea, because they have some interest in this region for shipping gas to Europe. So we built the platform and a first setup covering Kara Sea. So we are in the Arctic. This is the coast, the Siberian coast. And they wanted to go, when they were leaving the terminal here, the Yamal gas terminal, was it better to go directly through the Kara Gate, or was it better to go around Novaya Zemlya Island and to go to Europe? So the forecast was running operationally for 1 winter. That was to convince them that it was feasible to have that running operationally. It's forced by the ECMWF atmospheric forecast, the deterministic one, and by the Tapas ocean forecast that is available through CMEMS. We assimilate the concentration from AMSA2, which is a microwave-based data set. And we also assimilate the thin ice thickness from SMOS. So SMOS, it's a satellite that only see the ice when it's thin, and the signal is saturated for thick ice. You can find more information on this website, and what I will show now, it's an animation showing the analysis we got from the forecast system. So when you have a forecast system, you directly also get an analysis that is merging information from the satellite, from the data, and merging information from the model. So analyses are quite powerful because they are consistent with the data and consistent with the model physics. I'll show an animation for the sea ice thickness for 1 winter. This is just a snapshot in February. You see that we have sometimes large, high value of sea ice thickness, and this is due to the dynamic. We converge, and then it creates thick ice. The thermodynamics is also active. So the animation starts in fall. We freeze, we create sea ice, then we deform the sea ice during winter, and then we melt it during the melting season. There are also other nice features around island. So the situation upstream and downstream island is completely different. So let's start the animation. It's a bit quick. We are freezing up in fall. In winter, we deform the ice, so we create this band of thick ice. We also have a lot of thick ice north of Kara Sea, and this is important for shipping, but also for seasonal prediction, because this thick ice remains much longer in the in the in the melting season. So it's not only useful having the right sea ice dynamics. It's not only useful for operational forecast, but it's maybe also useful for seasonal forecast. So the platform was delivering data every day. So it was to prove that it was feasible. So we were delivering data maps on a website where you can choose the date you want, and you can visit the website and have a look yourself if you want. There are maps of concentration, sea ice thickness, and also the ratio of reached ice. So what is the percentage of ice that is reached? This is very important for shipping. And then we also provide the drift data were also available on FTP servers and on a data system. So they were actually using the data for planning, and they were quite happy with that. We also implemented an automatic evaluation of the forecast using AMSA2 sea ice concentration and the smooth thin ice thickness, but also we were also comparing to the OSISAF ice drift, which is a coarse resolution ice drift data that is available every day, and that is done by the Norwegian, by Met Norway. So this is an example on the left, comparing observed and simulated ice drift. It's always computed over 2 days, so it's the 2 days drift. And you see in red the observed value and in blue the simulated ones. We are going in the right direction. So that's qualitatively good. And now to have a more quantitative evaluation of the drift, we looked at the drift error for 3 months. For 3 months. So in blue, you have the mean drift error from the forecast for day +2 to day +7. So that's the length of our forecast. And we compared that to what was given by the persistence. So the persistence is just to take the ice drift of the day and to consider that the ice will continue to drift in the same direction for the whole period. So we were always better than the persistence for the ice drift, but it's not so surprising because wind is changing very quickly. So if you take the wind of one day and you consider it will be the same wind for the full week, it's not a good approximation at all. So it's never good to take persistence when you are looking at highly variable quantities. But still, comparing to persistence, it's one of the metrics used in the forecasting community. So that's the one we used also. From the comparison between the forecasters and the persistence, you can compute a skill score. You just take the difference between the RMSE of the persistence and the RMSE of the forecast, and you divide by the RMSE of the persistence. So it's a normalized score. If it's positive, it means that the forecast is bringing valuable information. If it's negative, it means that it's bad. And the closest to 1, the better you are. Thanks to this analysis, we found that the skill score was decreasing with time because the error was increasing with time. But this is normal because it's very difficult to predict the wind days in advance, and the ice drift is highly correlated to the wind. So to improve that, we need to improve the wind forecast. It's always easy to put the problem on other people. So it's not our fault. It's only because of the atmospheric forecast. So the people from Total were especially happy with the thickness field data produced by the system, because for them it was looking much more realistic than what was available from any other forecast system. So this is an example of the sea ice thickness from the Tapas system that use HICOM for the ocean, Chiche for the ice, and ensemble Kalman filter for the data assimilation. It's all smooth, even if the resolution is about 10 kilometers in that area. It's very smooth. Whereas in the case of the NERSC platform, it's much more heterogeneous. We see small features, but also we see thick ice upstream islands and thin ice downstream. So this is seen from the field. And this is very important for shipping, of course. So that was for the platform, and now I would like to tell a success story made with this platform. So the story started in July when we were contacted by SHOM. It's the Oceanography and Hydrography Service for the French Navy, because they wanted, or they asked us if we were able to provide real-time sea ice forecasting for a scientific covering Greenland Sea, for a scientific campaign that was planned for mid-August. So the deadline was quite short, and all my colleagues were on vacation. But I said, why not? Let's try. So the vessel is a non-ice class vessel, research vessel named Pourquoi pas, which means why not in French. So it's a non-ice class. So it means that they want to avoid any types of ice. That's they have to follow the regulation and also to ensure the safety of the people. And that's more or less the plan they had. They wanted to go as far north as they could and as far west as they could, knowing the constraint about the ice. And the favorite plan was to go at that location at 75 north and 15 west. So that was the favorite location. So the problem, we had to work a bit because in summer, in those areas, the thin ice is melting at the surface. It's thin ice mainly, and the concentration is low in that area. So we know that microwave-based data are completely useless for this type of questions. So to still provide useful forecast, we completely changed the assimilation to assimilate ice charts directly. And we were assimilating weekly ice charts as this one, but also daily ice charts that have less information. And we take both from the National Ice Center, so the US ones, because it covers the whole Arctic, so it's quite practical to use those. So this is an example just before the starting of the mission, and you can already see what will be the problem. They want to go there with a non-ice class vessel, and there is this big chunk of highly concentrated ice just north of that point. And in this region, the sea ice is drifting on average south. So there will be trouble to try to reach that point. To convince them that it was maybe problematic to go there, we were providing maps of sea ice concentration, thickness, and drift. And to make them more readable, we used color code from the Norwegian ice charts for the concentration and from the icebreaker classification from Bureau Veritas. So the maps were very easy to read, but they were also the data were also available in a NetCDF format. So it's a geo-reference regular grid format. So even if the mesh is moving, it's a pure Lagrangian model, the data were easy to use. So they used the data, the NetCDF files and the maps for planning. So they saw that at the beginning of the mission, there was highly concentrated ice at the location they wanted to go, and the forecast said that there would still be ice at that location 1 week after. So they decided to change the plan, and they went to Jan Mayen Island instead to do some measurement. But then they were really motivated to go west, so they went west, but they reached this band of highly concentrated ice. The band is also visible from SAR images that they were downloading when they were available. So you see this band of ice. So what they tried to do is to go around this band, because the forecast said that it was only a thin band, a narrow band of ice. So they tried to go south and then west and then south until they reached this point. So they were almost at the end of the band. But the problem is that there was fog coming and they had to move from the area. So they were not able to test if the forecast was very correct. So they had to move, and they went much more south to do other types of measurement. So they wrote a very nice report to us saying that the NERSC forecast have revealed precious insights in order to plan the mission. But they were also saying that maybe in the near future, this type of forecast will be the best estimate to use. So they said it would be better than ice charts and SAR images for 3 reasons, even 4. First, they are reliable for the ice patterns. So we can see the bands as they are. There is anticipation possible with those forecasts, because you have information for the future. It's available even with a low bandwidth satellite communication, and it's easily readable for non-specialists. It's not like SAR images that are quite difficult to analyze. So I think we convinced them that our forecast could be used. They just point a small problem about being too pessimistic for the low ice concentration, so from 0 to 30%. But this is clearly coming from an overestimation of the concentration from the NIC ice charts. So you see on the right, it's coming from NIC. They say that in this area, in green, the concentration is between 10 and 30%, whereas in the Norwegian ice charts for the same area, it's in blue, light blue. It means that it's between 0 and 10% of concentration. So the overestimation, again, it's not our fault. It's only due to others. And we can easily solve that by also assimilating Norwegian ice chart in the system when they are available, so only during weekdays. The weekend, it's free time for Norwegian. So what is good, though, is that both systems, so the ice chart from NIS and NIC, they both agree on the position of the open water limit. So that's the limit you should not cross if you have a non-ice class vessel. So both of them agree on that, and that's very important for many people. So let's be a bit provocative now, and let's look at what was available on the Copernicus marine service system. So we had the Tapas forecast producing sea ice concentration map for the same day as the ice chart. So in red, it's the limit, the open water limit we just defined from the ice chart. And Tapas says that actually, no, there is no sea ice over there. You could go there. It's no risk at all. So, okay. If you trust, if you take information from the global forecast system, ice ocean forecast system, then they would say the same. No, there is no sea ice. Go on. Whereas actually, the ice charts both, they show that all this region has ice that can be highly concentrated and very dangerous for non-ice class vessel. So that's the end of the provocation. So we learned a lot about from this experience, because if you have a forecast system, it means that you also got an analysis. So the analysis is merging data and model. So you can look at how the sea ice concentration from the analysis looks like. So this is the initial field, merging data from observation, so satellite observation, ice charts, but also reanalysis or forecasting systems. So that's how it evolved from July to end of June. You can see there is a large variability near the ice edge. It's moving a lot over there. You see also nice structures that are sometimes preserved by the assimilation. And what you can do also is to look at the updates. So every day you update the model state towards observation. So you can just look at the update. If it's in red, it means that you remove some ice. In blue, you add some ice to be closer to the observation. So this is the update for 2 months. We generally see large updates, so higher values along the ice edge, because there is a large variability in the system. So it's difficult to forecast that properly. But you could also, maybe I restart that one, see high values of the updates on the linear features that are simulated by the model, because those are not seen by the ice chart. So we could maybe improve that later. So what you can do also, and what we did, is to just look at time series. And from that, we identified a bias in the system, and we found that the bias is most probably coming from a bias in the near surface air temperature coming from the weather forecast. So we tried to correct that. The first try was to just decrease the temperature from the forecast by 10 degrees, and it was very good for the first part. So for July, it was quite good. But then in August, we had this persistent bias. So the correction was always negative. So the system was always removing sea ice to go towards observation. So we made a second try with -5, and it was then better for August. But this is boring to try to correct biases manually. It's time consuming. It's never ending. It's not satisfactory. So what we did instead is to start playing with data bias-aware data assimilation. And that's what I will just present now. How much time do I have left? Not too much. Okay. So I'll go very quickly. If you have a persistent bias, it means that you will always correct in the same direction. So you will have this sawtooth profile in some of the quantities you are looking at. You will have also the mean update that will be not centered around 0. So that indicates that you have a bias. Let's go faster. So the idea behind bias-aware data assimilation system is to use this information. If you are always correcting in the same direction, you know that there is a bias, and you will try to correct that. You need a control parameter, and in our case, we choose the control parameter to be the near surface, a correction on the near surface air temperature. That's how the correction evolves through time. We start with the value from the reference run -10. In July, the system was staying more or less around -10. But then in August, it directly moved to values closer to -5. So it's more or less consistent with what we found manually, but it's all done automatically. So what is good is that it removes this sawtooth profile automatically. So you don't have these ugly features anymore. It also removed the bias, so the mean update is now centered around 0. And it has also a positive effect on the RMSE. So this is the RMSE before, and this is the RMSE with the bias-aware data assimilation scheme. So this is just a snapshot. I took a very bad example with the reference run. We remove a lot of ice. So this is the update where we remove a lot of ice from the system. And here it's the same field for the BADA, bias-aware data assimilation system. We still remove some ice, but we add some ice, and the mean is much closer to 0 than with the persistent bias. So if you have better ideas, just don't hesitate to tell me. We are not experts in data assimilation. So the last question, I have only 3 slides. Can we forecast local sea ice deformation? Sea ice drift are available at high resolution. It covers the whole Arctic, and it's available daily from Sentinel SAR images through, for example, the Copernicus Marine Service. So from the sea ice drift, you can compute sea ice deformation, and you see all these bands of very active deformation zone. So the idea is to try to assimilate that, to use this information, because it's quite persistent. When it's deforming, it will be deforming for the next days. So what we did as a first try is to start from the deformation from observation. So it's a deformation field from the RGPS system. And we know from the model that only damaged sea ice deforms. So using this information and correlation we found with the model, we built a damage field that is consistent with the data. And then we feed the model with initial conditions based on this damage field. And we run the model for the same period, so for this period in March. And what we found was quite promising. So we can reproduce most of the features at the right location and also with the right magnitude. And what was also super nice is that I made some mistake in computing or defining the mask for the model. So I wanted to have exactly the same mask, but actually it was not exactly the same mask for the model. And what is nice is that you can see what happened when there is holes in the observation. What is doing the model? It's just filling the gap consistently with the physics with nothing else to do. It's just you put that in the model. It will try to minimize the energy, blah, blah. So you will have these very nice features appearing automatically. So conclusions and perspectives. It's fun to do modeling. It's fun to do observation. It's fun to do data assimilation. But it's much more fun to do the 3 at the same time, because you cannot be so far from reality. Perspectives are coupling, subgrid scale parameterization to link different data sets, to go for more operationalization, and to develop new data assimilation method. So if you are interested, please visit our website. And also, if you think it's a nice topic, don't hesitate to share the presentation, to discuss that with your colleagues, supervisor, friends, because it's not always easy to get support for new ideas. So we are always open to new collaborations. Thank you.
So one lesson, it's important to make mistakes, right?
It's very important to make mistakes. And many people do mistakes, so don't trust what you get, just check it yourself.
Yeah. So errors is the way to the truth. Yeah. Any question?
Thank you for the good presentation. And what's the weather forecast model resolution? Do you know? And
it's the standard ECMWF deterministic forecast. Who knows? 20, 30 kilometer? I don't know.
So consider that there is an error in the weather forecast. Do you intend to do your own weather forecast?
I think that's clearly too heavy. But what you can do, usually it's the near surface information that can be biased. But the information that are much higher level, like 100 meter, they are not biased. It's because the near surface temperature, wind, they are mostly coming from parametrization. And if you don't see the same sea ice as in reality, you will have just the wrong temperature, the wrong wind, and so on. So the best is to take information from the 100 meter and to have a small model for the boundary layer, and then you get maybe better information that are consistent with your sea ice.
I see, thank you.
Something else? Could you tell a little more about what you said CMMS is wrong? Why? Have you looked at that?
Yeah, I think it's the explanation is quite easy. At this moment of the year, we are in summer in a low concentration area with thin ice. So if you use information only from microwave-based data, whatever the system you use, the data assimilation system you use, and so on, the information you feed your model with are biased. So you will not be able to reproduce reality.
So the reason is, essentially microwaves data.
Yes.
Actually.
So,
Okay.
so the solution would be to just take also ice charts in the data assimilation scheme. And that would really improve the information provided by those services.
Okay. Yeah. Christina?
I might have missed it, but what kind of setup data were used to detect sea ice, and what are the cause of the noises?
So the cause of the biases, it's due to the sensor. When you have microwave sensor, actually you get only information at the surface, because microwave are just reflected by the surface. So if there is just a bit of melted ice at the surface, if you have often the ice is melting, it's forming pounds on top of the ice. So if you have that, those satellites or those sensors will think that there is only open water everywhere, and they don't see the sea ice below. So that's one of the reasons. The other reasons are mixing signals that makes the open water signals is much stronger. So for low concentration area, they will think that there is no ice at all, even if there is. And then the resolution of the sensors. And the data we use for the microwave-based data, they are either coming from AMSA2, AMSA3, I don't remember all the name, but yeah.
Okay. Thank you, Sylvain. Thanks again.